Hi, this is Mrs. LaBarbera. Here's another example from past AP exam from 1998, question number 3. Block 1 of mass M1 is placed on block 2 of mass M2, which is then placed on a table. A string connecting block 2 to a hanging mass M passes over a pulley attached to one end of the table as shown. The mass and friction of the pulley are negligible. The coefficients of friction between block 1 and 2 and between block 2 and the tabletop are non-zero and are given in the following table. Here's static friction, mu S1, and static friction, mu S2. Mu S2 is between block 2 and the table, mu S1 is between block 1 and block 2, and the kinetic friction of the two surfaces. Express your answers in terms of the masses. That means M1, M2, and M. Coefficients of friction, mu S1, mu K1, mu S2, mu K2, and G, the acceleration due to gravity. A. Suppose that value of M is small enough that blocks remain at rest when released. At rest means the sum of the forces has to be 0. For each of the following force, determine the magnitude of the force and draw a vector on the block provided to indicate the direction of the force if it is non-zero. So only draw it if it's not 0. First one, the normal force N1 exerted on block 1 by block 2. So on block 1 by block 2, that force should be upward. And that normal force should be equals to M1G, should be equals to the force Earth exerted on block 1. The two forces cancels out. So that's why block 1 is not moving in the vertical direction. Friction F1 exerted on block 1 by block 2. Now since block 1 and block 2 are at rest relative to each other, so none of them are accelerating. There's no force between the two, no horizontal force between the two. So F1 equals to 0. Since it is 0, there is no arrow. You can't show an arrow for a 0 quantity. Next, the force T exerted on block 2 by the string. So again, on block 2, think about what are the forces in the horizontal direction. You have tension, T, and another force is the friction from the table to M2, since there is no friction between M1 and M2. So those are the two forces. Those are the two forces has to be the same. And on big M, since M is at rest, the gravity force on big M and the tension force on big M has to be the same. These two forces, the tension on the string has to be the same. So the force on T2 has to be the same as on big M. And on big M, we know that is just mg. So T equals mg. Next one, the normal force N2 exerted on block 2 by the tabletop. On block 2 by the tabletop have to support the weight of M1 and M2. So that N2 equals to M1 plus M2G. It's going upward. The friction force F2 exerted on block 2 by the tabletop. Again, we talked it before, the friction force has to be equals to this tension force. So the friction force equals to M times G. This force of friction is static friction. And we know static friction changes. As you increase the mass of M, it's going to get bigger and bigger until it reaches that crucial value called the maximum static friction. Then the block will start to move. Let's take a look at part 2. So, determine the largest value of M for which the blocks can remain at rest. This is the crucial value. The largest value is mg has to be equals to maximum static friction on M2. So the 2 has to be the same. That's the largest possible value. F static friction on M2 has to be equals to mg. So that's how you figure out M. So M, you cancel out G, M equals to mu S2, M1 plus M2. C. Now suppose M is large enough that a hanging block descends when the blocks are released. Assume block 1 and 2 are moving as a unit. No slippage, determine the magnitude A of their acceleration. Now it's large enough, it starts to accelerate. So let's see what happens. If it starts to accelerate, take a look at, first, in order to find acceleration, let's draw a free body diagram. Free body diagram on big M, still again, you'll have two forces. You have gravity force, which is big M times G, and you have tension is upward. The net force on big M equals to big M times acceleration. Because M1 and M2 are moving as a unit, so we are treating the two as one object. On this object, there's gravity force, M1 plus M2 times G. There is N2, the normal force from the table supporting the two blocks. So these two forces are the same. There is also tension force to the right and friction from the table to M2 to the left. This friction is kinetic friction because the blocks are moving. So the net force of this system should be, gives you M times A. So you write two equations. Big mg minus t equals big M times A, and the net force T minus K2, T minus FK2 equals M1 plus M2A. What is FK2? What's the friction? Friction equals to mu K2 times N2, and N2 is M1 plus M2G. So we combine these two equations by adding them. mg minus fk2. fk2 is just mu k2 times m1 plus m2g. Then that equals to, we add all the terms on the left. Big M plus m1 plus m2 times a. And from here, we can solve for a. So a is just this. This is all in terms of the masses and mu plus, and the gravitational constant. Next question. Now suppose that big M is large enough, it's so large that hanging block descends block 1 is slipping on block 2. Determine each of the following. Magnitude A1 of acceleration of block 1 and magnitude A2 of acceleration of block 2. So whenever you have to determine acceleration, the first thing you do is to draw a free body diagram. Let's take the free body diagram of M1. What are the forces acting on it? So we know definitely have gravity. We know there's a normal force M1. But what is the force cause M1 to accelerate? It has to be the friction between M2 and M1. And that friction has to be to the right. And this friction, because it's moving, so it's kinetic friction. So the net force is the friction, and this friction causes the acceleration. So M1 A1 equals to mu K1 M1 G. And from here, you can solve A1 equals to mu K1 times G. It's to the right. It's in the same direction as the friction. Now let's calculate magnitude A2 of acceleration of block 2. Again, to calculate acceleration, we have to draw a free body diagram. Here are the forces on M2. There is friction force produced M1 from M1 on M2, the friction from the table on M2. There's gravity on M2 plus the M1 also have a pressing force on M2 downward. There's N2 from the table on M2 and a tension of T on M2. This tension is the same tension as on big M. Then on big M, besides the tension, there's gravity on big M. So the net force equals to MA. The net force on M2, which is M2 times A2, that equals to T minus FK1 minus FK2. Because we know up and down cancels, the M2 is not moving in the vertical direction. So FK2 is mu K2 times N2. N2 equals to M1 plus M2G. And FK1 is just mu K1 M1G. By the way, FK1 has, and FK1 on M2 is the same as FK1 on M1. Those are action-reaction forces. One acting on M1 to the right, the other force is acting on M2 to the left. So the two forces acting on different bodies has the same magnitude and opposite direction, according to Newton's third law. Here is the net force on big M. Big M A2 equals mg minus c. One way to easily solve this is to add equations on the left. That should be equals to the sum of the two equations on the right. So on the left, you have m2, a2 plus big M a2. You're factoring a2 out, then you'll have this sum, big M plus m2. On the left side, on the right side, you have t and t cancels, and this is the term you will have. After you factoring g out, big M minus mu k2, m1 plus m2 minus mu k1 times m1. That's it. That's A2. I hope it helps. Thanks for watching.